Today I will be talking about freeze-dried hot start PCR mixes, the evolution of molecular diagnostics. I'll tell you a little bit about molecular diagnostic assay requirements, and then talk to you more about a novel hot start tool, which is hot start dNTPs. I'll go into detail about the mechanism and how they perform, show you data for improved performance over standard dNTPs, then talk to you about the versatility and compatibility when you use hot start dNTPs in a variety of biological assays. I'll go more into specifics about the application of hot start dNTPs to reverse transcription PCR or RT-PCR. Then I'll describe the process of freeze drying and tell you why you might want to freeze dry some of your assays. And I'll walk you through a workflow in which you would freeze dry an assay. More specifically, I would show you how to design a freeze-dried assay that would be suitable for molecular diagnostics. So the goal in molecular diagnostics is to detect a biological marker, either through the mode of genomics or proteomics. And you would want a few different things out of your assay. You would like it to be robust so that you can amplify low levels of input of the biological marker, and you would like it to be specific so that you're not getting any off-target reactions forming, and then you are only amplifying the desired target. You would want your assays to be reliable and reproducible, and also have a simple workflow so that you wouldn't introduce any contamination during your setup, and you would reduce any human error that could occur. I'll be focusing mostly today on the nucleic acid detection methods, or the genomic methods. These can be microarray analysis, PCR amplifications including endpoint and real-time. I'll also talk about hot start technologies and how this can be an important diagnostic tool. Hot start methods are specifically used to improve amplification specificity in stringent applications. They sequester individual components of your reaction and prevent the reaction from starting at your typical setup conditions, such as room temperature. With this, they improve the amplification specificity by decreasing any mispriming or primer-dimer and off-target reactions that could occur, and take away from your amplification of your desired target. There are a variety of common hot start methods out there, including hot start primers, and most commonly hot start DNA polymerases. However, if you are doing a specific assay, you might need a more specific DNA polymerase, such as one with higher fidelity or one that can amplify longer targets. In the case where this DNA polymerase that you need for a specific assay is not available in a hot start version, you may have to design one of your own, which could be costly and time-consuming. So today I want to talk to you more about a more universal hot start method called hot start dNTPs, or CleanAmpdNTPs. CleanAmpdNTPs have a thermolabile protecting group on the 3' hydroxyl of the sugar. At this point, they're not a good substrate for the DNA polymerase. So when you are setting up your reactions at room temperature, they will not incorporate. Once you ramp up to higher temperatures, such as 95 degrees for a PCR reaction, the thermolabile group simply falls off and you end up with the corresponding standard dNTP. Your amplification of your desired target can then start happening because a standard dNTP is a suitable substrate for the DNA polymerase. Here is some older data that shows the improvement using CleanAmpdNTPs over the use of standard dNTPs. So keep in mind throughout the presentation that we have used challenging targets that you would actually need a hot start in order to be able to amplify your desired target. So on the left there's a gel which uses standard dNTPs and a number of different DNA polymerases which are not hot start. So for whatever reason you may pick a specific DNA polymerase for your specific assay. But as you can see with standard dNTPs, you don't always get amplification of your desired target. You often get primer-dimer and mispriming happening in your reactions. And so instead of making one of these a hot start DNA polymerase, you could in fact use CleanAmpdNTPs. So the gel on the right is CleanAmpdNTPs used with a variety of the same DNA polymerases. And in this case you see improved amplification of only your desired target in each one of the reactions, with a decrease in primer-dimer and mispriming. So CleanAmpdNTPs is compatible with a number of DNA polymerases and also helps to improve their performance. CleanAmpdNTPs are extremely versatile. You can pretty much make any assay a hot start. To date, we have done several different experiments with the CleanAmpdNTPs. We've amplified by endpoint targets up to 20 kb in length. We've done real-time PCR experiments in which we've used standard cycling, which takes about an hour and a half, or faster cycling, which you can get your results in about 30 minutes. We've also done multiplex endpoint PCR up to 7 targets at the same time, or we've done fast multiplex PCR in a real-time machine where you can see 3 targets amplifying in real time at the same time. More notably, you can apply the CleanAmp thermolabile protecting group to a number of different dNTP analogs. 7-deaza-DGTP is a modified analog that people typically use in the amplification of GC-rich targets. We currently have a CleanAmp 7-deaza-DGTP, which can amplify GC-rich targets up to 90% in GC content. Once you amplify these targets, it effectively linearizes your target and prevents any Hoogsteen base pairing from occurring, but does not interfere with the Watson-Crick base pairing. This in turn improves the later downstream applications like Sanger dideoxy sequencing by allowing those sequencing traces to be more distinct. CleanAmp can also be applied to DUTP, which can be used in PC carryover decontamination with UNG. And I will go more into detail about the application of CleanAmpdNTPs to reverse transcription PCR or RT-PCR. So people typically want to use a hot start method for PCR, but there are not a lot of available methods out there to make the RT hot start in an RT-PCR. So we wanted to investigate whether there was a need for a hot start step at the RT step as well as the PCR step. So in these few reactions, you can see in the first lane, I use standard dNTPs with a standard Taq DNA polymerase. So neither the RT step or the PCR step was hot start. And what you end up with is amplification mostly for mispriming reactions and side products, but hardly any amplification of your desired target. Then the next lane, I added in a hot start DNA polymerase, which just made the PCR step hot start. And as you can see, there's not much improvement with just making the PCR step hot start. So this gave us good indication that there was a necessity for a hot start at the RT step. Next, we wanted to look at whether it was feasible to use CleanAmpdNTPs to provide this hot start at the RT step. So we wanted to test whether CleanAmpdNTPs would shut off the reaction at room temperature setup conditions, which is 25 degrees. And then also, would it deprotect enough in order to amplify at 50 degrees or give you an RT target? So this is a primer extension reaction in which the primer is labeled with a FAM dye. And I've compared both standard and CleanAmpdNTPs. At 25 degrees, the standard dNTPs provide a full-length target formed. However, the CleanAmpdNTPs, there is no indication of a target being formed, which is good indication that your reaction is completely shut down at this temperature. When doing this reaction at 50 degrees, which is a typical RT temperature, you get full-length product formed when using standard dNTPs, as well as full-length product formed when using the CleanAmpdNTP. So circling back and revisiting those reactions you saw before in which there was no hot start at all, or there was a hot start method at the PCR step. We now look to the third lane in which CleanAmpdNTPs were used, which provide a hot start at the RT step as well as the PCR step. And what you find is that only your desired target is amplified and you have a robust target forming with a decrease in mispriming and side products. So not only are CleanAmpdNTPs compatible with a number of DNA polymerases, they also are compatible with a variety of reverse transcriptase enzymes. So the gel on the left is showing a superscript 2 reverse transcriptase enzyme with the use of either standard or CleanAmpdNTPs. These reactions were done at 42 degrees. With the standard dNTPs, again you get mostly off-target reactions occurring. However, the CleanAmpdNTPs improve the amplification of this target. MMLV RNase H- was also used, which is very similar to superscript 2. In this case, the CleanAmpdNTPs improve the reaction as well. Many people will often use superscript 3 so that they can do RT reactions at higher temperatures to get rid of any RNA secondary structure and improve your reaction. So you can see with standard dNTPs, you do get an improvement with using this superscript 3, where you do get target formation, but you do have a bit of side products still forming. However, when you use the CleanAmpdNTPs along with the superscript 3, you get only robust target formation happening. Next, we wanted to look at the limit of detection of using CleanAmpdNTPs in a quantitative real-time RT-PCR assay. So we did a standard curve using total liver RNA with an input of 500 nanograms all the way down to 32 picograms. We could say that you were able to amplify low levels of those biological markers using CleanAmpdNTPs in an RT-PCR. We then wanted to challenge the system to not only amplify singleplex reactions, but to see if we could also do multiplex reactions. So we looked at 4 different targets and used the standard dNTPs in the singleplex reactions of all 4 different targets. And then in the last lane, you have all 4 targets to amplify at the same time. With standard dNTPs, these challenging targets are not often amplified cleanly and robustly. And once you get to the multiplex, they are definitely not all amplified at the same time. However, with the CleanAmpdNTPs, you amplify each target specifically, and then you are also able to amplify all 4 targets at the same time in equal quantities. Next, we wanted to benchmark against commercially available one-step RT-PCR kits that were out on the market today. Again, the CleanAmpdNTPs can amplify all 4 targets at the same time. However, 3 other commercially available kits were not able to amplify all 4 targets at the same time. So CleanAmpdNTPs are being used in a variety of diagnostic applications out on the market today. We are currently working with a company called Biofortuna. We are collaborating with them to make some dried down PCR master mixes. They already have a HLA typing kit, which is freeze dried and is available and uses CleanAmpdNTPs. However, they specialize in the freeze-dried molecular diagnostics assays. They do a variety of formats, including 8-well strips, multi-well plates, POC cartridges, and microfluidic devices. Their specialization is really in the lyophilization of these assays. So to tell you a little bit about the freeze-drying process. Freeze-drying is a dehydration process to preserve biological compounds or assays. You start with freezing your material. You then slowly warm your material to cause sublimation of the ice. You then want to heat above room temperature. And what you end up with is a lyophilized pellet. This pellet is now temperature stabilized product and can be stored at ambient temperature. Hydration of this pellet reactivates your compounds to full biological activity. So there are a number of benefits to freeze drying your assay. The number 1 benefit would be simplicity of a one-step workflow. So on the top part, we have a traditional methodology in which you must freeze and thaw each one of your components that goes into your assay several times. There's a lot of pipetting, a lot of mixing, and a lot of transfer of material from one tube to another. In this entire process, this can introduce potential human error and potential outside contamination. In the freeze-dried assay methodology, you have everything you need for your assay dried down in your PCR tubes or whatever format of your choice. And all you need to do is add your DNA to rehydrate your pellet and activate your compound. Then your reactions are ready to put in the thermal cycler. A second added benefit is stability. You're able to store these freeze-dried assays at ambient temperature for up to a year. Here I show you some data of an accelerated stability study in which these assays were actually stored at 37 degrees, which is an extreme storage temperature. And what it's comparing is at week 1 after being stored at 37 versus week 26 being stored at 37 degrees. And so this just shows you that this data is comparable and that these biological assays have not been affected, even at extreme storage conditions. This can be useful also for transporting devices. They can be used for POC devices so you don't have to worry about taking these out to the field and keeping them at a low temperature. Another benefit is the manufacturing precision that goes into the drying down of your assay, which is due to Biofortuna. So this is a typical workflow of drying down your assay. You would start with combining all of your ingredients in a large volume. You would then dispense to a, say, a PCR plate or whatever format you choose. Then Biofortuna would optimize a specific lyophilization protocol specific to your assay. And what you end up with is your packaged complete PCR assay. And one of the reasons they use CleanAmpdNTPs in these processes is because your compounds are often sitting in these conditions for a couple hours. And the CleanAmpdNTPs really help from anything starting in your reaction and can prevent things like primer dimer. Another benefit is improved assay efficiency and specificity. On the left we have real-time curves that show improved PCR efficiency, where Biofortuna took one of their freeze-dried master mixes which contained CleanAmpdNTPs and put it head-to-head against a competitor's hot start TAC master mix. So as you can see, you get a little bit earlier CQ value from the freeze-dried master mix and a little bit higher amplification. Also, you get improved specificity with freeze-dried master mixes. So the amplification of the target is pretty similar between Biofortuna's mix and the competitor's mix. But when you look at the negative control, or the NTC, you see that the competitor's mix, which is the dotted gray lines, are actually popping up, whereas the Biofortuna's mix, which is the dotted blue lines, is flat lines, so the NTCs are not popping up. So there's no off-target going on in the Biofortuna mix reactions. So overall, the benefits of freeze drying an assay are the simplicity of the one-step workflow, the stability, the manufacturing precision that is involved, and to improve your assay efficiency and specificity. I now want to walk you through how you would convert a wet assay to a freeze-dried assay format. And there are a number of steps involved. The first step would be to test the feasibility of the different assay components that you would need to change over to for a freeze-dried assay. You would then want to optimize these new assay components and assay conditions. You would then look at lyophilization feasibility and test a number of cryopreservatives, followed by lyophilization analysis and validation, and finally stability studies. So to test out the feasibility of assay components, some common assay components are not compatible with freeze drying. So if you look at the ingredients in a wet assay, one of the main ingredients is the enzymes, which usually contain glycerol. So to convert over to a dry assay, you would want to switch from glycerol-containing enzymes to glycerol-free enzymes. Another common component which might be included in master mixes to help with stability is DMSO or other types of organic solvents. Organic solvents don't dry down well, and so you'd want to try to take these out of your reaction. And so with testing these different assay components, you want to see that you don't lose any efficiency or amplification ability when you change over to your dried down assay. So in blue you have the wet assay, which contains the DMSO. The gray lines don't include the DMSO and would be more comparable to what you would have in a dry assay. So as you can see, these assays are pretty comparable, and so you could take out the DMSO without inhibiting the reaction. Secondly, you want to look into converting over to the glycerol-free enzymes. So in red you have the wet assay, which contain both of the glycerol-containing enzymes. In gray is the incorporation of the glycerol-free RT enzyme, and in black is the incorporation of both the glycerol-free RT and the glycerol-free TAC enzyme. So here you start to see, when changing different components of your assay, you start to see different inhibitions of the reaction. So once you add in both of the enzymes that are glycerol-free, you get a delay in CQ. It is at this point that you want to go through optimization steps to see if you can optimize these new components to get back to the full functioning of your wet assay. So this is just one example of an optimization that you would do for the assay conditions. So these actually include the glycerol-free enzymes, and this is a magnesium titration to see at which concentration of magnesium your assay functions the best. So we went from 3 millimolar up to 4.5 millimolar magnesium. And if you look at it just by real time, all of the reactions look very comparable. However, we ran these on an endpoint gel, and you can see that at the higher levels of magnesium, you're actually getting a few mispriming products amplifying, which you don't want in a molecular diagnostics assay. And so you would want to choose one of the lower levels of magnesium concentration so you can still stick with and get that specificity that you're looking for. There were a number of different optimization steps that we have already gone through, and I didn't show you all those today. That was just one set of them. But this is where we are with the conversion of our wet assay to our dried assay. So we have actually optimized quite a few things, and the dry assay is pretty comparable now to the wet assay. So moving into testing the lyophilization feasibility with our new assay conditions, there's a number of cryopreservative formulations that Biofortuna has. And depending on your assay, one or more of these might work better or might inhibit your assay, and so you need to test them. So you take your optimized assay and you then throw in each one of these different cryopreservatives to see how it affects your reaction. So in green is the original optimized dried assay format, and then the other three are each cryopreservative added in one at a time. As you can see, most of these reactions by real time are extremely comparable. In fact, adding in the cryopreservatives actually lowers the CQ of the optimized dried assay closer to where your wet assay CQs lie. And there's very little difference in between the different cryopreservatives. So in this case, we leave it up to Biofortuna to choose which one of these cryopreservatives might be best for this assay, considering none of them affect the assay all that much. Another thing that Biofortuna really has a hand in is looking at the lyophilization protocol of your assay. So they use a number of analytic techniques in order to choose critical temperatures at which they dry down your components. One of these is freeze drying microscopy, and this will help them define specific temperatures that they use in the lyophilization process. Another analytic is differential scanning calorimetry, which also gives them critical temperatures to use in this lyophilization protocol. Next, you would want to do a lyophilization validation followed by stability studies. The lyophilization validation is basically to confirm that your freeze-dried assay is still offering stability and has not compromised any performance. So on the left, you have some real-time curves from before and after freeze-drying your master mix. And these are very comparable, so you haven't lost any functionality from the freeze-dry. You then take your freeze-dried master mix and put it through a standard curve and find that it does still retain the sensitivity that you need. Once you have done this and the validation of the lyophilization has been done, you can go through stability studies to see how you can store your biological assay and how long you can store it at certain temperatures. So molecular diagnostics assays require robust, reliable, simple, and error-free platforms. CleanAmpdNTPs are extremely versatile, and they can be a reliable diagnostic tool which can easily be incorporated into many biological assays. CleanAmpdNTPs can be a more universal hot start method that improves the specificity of assays as well as enzymes. CleanAmpdNTPs provide a hot start method which is required during both the RT and the PCR steps to ensure robust and specific target amplification during RT-PCR. Freeze-dried assays offer distinct advantages over wet assays, such as simple workflows, stability, and reproducibility. The CleanAmpdNTPs and Biofortuna freeze-dried assay combination and design can create the ideal diagnostics. Thank you.